Let us start our today's session from hydrocarbons. The topic is alkyne, but before go with alkyne, let us complete just two more topics from alkene. One is the preparation of cis and trans alkenes. Yesterday we have seen it, but just I forgot to inform about the formation of cis and trans form depends on the reagent what we have taken. See, when I take but2ene, the name of the compound is but2ine. So, when I take but2ine, in presence of Lindlar's catalyst, say the palladium with charcoal, this is called palladized deactivated charcoal. It gives rise to the cis form of but2ene. Cis form, the two similar groups or the two identical groups are of same side of doubly bonded carbon. Suppose instead of Lindlar's catalyst, if we take sodium in liquid ammonia, we will get the trans form of but2ene. So, when but2ine is treated with sodium in liquid ammonia, the addition of hydrogen takes place in C triple bond C system such a way to form trans but2ene. So, trans form where the similar groups are of diagonally opposite to each other. So, this is one, and the next one from chemical properties. So, from chemical properties I have to discuss about the addition of sulfuric acid. Sulfuric acid formula H2SO4, in which from chemical properties, just I would like to discuss about addition of sulfuric acid. Sulfuric acid, actually the structure of sulfuric acid is this is H2SO4. This is what the structure of sulfuric acid, from which it has two hydrogen that is present as OH group and the sulfur with the two more oxygen atom. So, this sulfuric acid that can be written such a way, HOSO2OH. See, HOSO2OH. This is what taken in their structural form itself. So, the doubly bonded carbon in which the pi electron that attracts that hydrogen of sulfuric acid. So, one of the CH2 goes to CH3, the rest OSO2OH just adds with another carbon. So, we can write this is 2 here. So, we are getting CH3 CH2 OSO2OH. The same compound that can also be written as CH3 CH2 HSO4. The name of the compound is ethyl hydrogen sulfate. That's all from alkene. Now let us start the next topic of hydrocarbons, alkynes. Alkynes are generally called as acetylenes. Alkanes we said paraffins. Alkenes we said olefins. Similarly, alkynes they are generally termed as acetylenes, and their general formula is, the homologous formula is CnH2n minus 2. When you compare the CnH2n minus 2 with alkene CnH2n and alkane H2n plus 2 CnH2n plus 2. You can compare the number of hydrogen among the three types of hydrocarbon, alkyne, alkene and alkane. We may find the alkynes are having only 2 hydrogen atom, which is lesser than alkane by 4 hydrogen atoms. Similarly, alkene to alkyne 2 hydrogen atoms are differed. And this acetylene is well known about the name of oxyacetylene flame. This oxyacetylene flame is nothing but used for the welding purposes, in which the acetylene is mixed with oxygen. So, upon combustion of acetylene, a large amount of heat will be produced that can be used for welding the material. So, let us find the nomenclature of alkynes. So nomenclature, we have to name the compound. So the first member of alkyne family is from the general formula CnH2n minus 2, where n equal to 1 we have C2H2. So this is CH triple bond CH. This is what? Acetylene. So acetylene is common name and its IUPAC name will be, as it has 2 carbon atom, root word eth, so the name is eth and its suffix goes "ine." So the IUPAC name of CH triple bond CH is ethine. Now you can replace both of the hydrogen by any other alkyl group. Based on that we can have their homologous series. Let us take the first hydrogen by methyl group. So CH3, C triple bond CH. So this is called, its common name, methyl acetylene. Because one of the group is methyl, so the common name that makes it is methyl acetylene. How many carbon? It has 3 carbon atoms. So it has the prop as the root word and it has 1 triple bond. So it makes a propyne, its IUPAC name. So this is common name and this is what? IUPAC name. So we can write similarly the other molecule also. Let us replace other hydrogen by one more methyl group. So let us take CH3, C triple bond, C, CH3. So here we have 2 methyl group. So the common name it says dimethyl acetylene. So its IUPAC name will be, it has 2 methyl group, 4 carbon atom totally, but the position of triple bond is at 2nd carbon. So the name it becomes the 4 carbon that makes but and the position of triple bond is at 2nd. So the name it becomes but2ine. And we can write isomer of the compound CH3, CH2, C triple bond CH. See, this side I have ethyl, this side I have acetylene. So the common name it becomes ethyl acetylene. But IUPAC name, numbering the 1, 2, 3, 4. So the 4 carbon, it has a triple bond at the first position. So the name it becomes but1ine. So these two are isomer because it changes its position of triple bond from 1 to 2. So we can say these two make position isomer as they are differ in their triple bond. And we can have the ethyl group in place of one hydrogen. So we can write CH3, CH2, C triple bond, CH2, CH3. See that we have 2 ethyl groups. So the name we can write diethyl acetylene for its common name. But IUPAC name, let us start the numbering 1, 2, 3, 4, 5, 6. Or 1, 2, 3, 4, 5, 6. So on either of direction the triple bond takes the same position 3, 4. So we can write as it has 6 carbon atom hex and the position of triple bond is at 3rd one. So we can write hex 3ine. Not supposed to take 4 because the 4 is the greater number than that of 3. So that makes hex 3ine. So such a way we can name the derivative, the successive member of homologous series of alkynes. Let us see isomerism. Same molecular formula but different structural formula. So CnH2n minus 2 where n equal to 5 carbon. So let us write C5H 10 minus 2 8. So we are getting C5H8. For this C5H8, let us write the different isomer. So we can have CH3, CH2, C triple bond CH. So we have C5, 3, 5, 7, 8. So C5H8 we got. What about its name of the one? 1, 2, 3, 4, 5. So it has 5 carbon. So its root term is pent and the position of triple bond is 1. So we can write this is pent 1ine. So this one, it has a propyl group in its structure. We can write the chain isomer for the propyl. So we can alter CH3, CH, CH3, C triple bond CH. See, once again the position of triple bond to the same, but the length of the carbon that alters to 4 into 3. So this is 4 carbon in its chain. So that is butane, but in the third position we have the methyl group. So the name is 3-methyl but. The first position triple bond, so it makes but 1 ine. Or we can make the position isomer, because in both the cases we find the triple bond at first position. Let us change the position of triple bond. CH3, CH2, CH, C triple bond, C, CH3. See that? Same 5 carbon, 8 hydrogen, but the position of first triple bond it brings to 1, 2, 3, 4, 5. So the position of triple bond from first to second it has shifted. So we can write the name of the compound is pent. The position of triple bond at 2, so the name it becomes pent 2-ine. So for the same given molecular formula, we can write the possible isomer. The first two, they do differ in their length of chain, so that makes chain isomerism. But the second one that makes that position isomer with respect to the first one, so this shows a position isomer of the first two. So similarly, we can write the possible number of chain isomerism and position isomerism for the given molecular formula. Let us discuss about the structure of alkyne. Alkyne, it has carbon-carbon triple bond. One of the bond is sigma, the other two bonds are pi bond. So as a result of the sp hybridization, that molecule it attains the linear shape with the bond angle of 180 degree. Where carbon-carbon bond length is found to be 120 picometer and its bond enthalpy is 823 kilojoule per mole due to the triple bond system. And between the two carbon atom we can observe the presence of one sigma bond and two pi bonds. How the sigma bond and two pi bonds are formed between the carbon atom, that can be explained by sp hybridization. Carbon, it has 6 atomic number and 2 of the electron belongs to the helium inert core and rest of 4 electron is present in its 2s and 2p orbital. The 2s electron of carbon that mixes with, that goes excited to 2p orbital, where you are getting 2s1, 2px1, 2py1 and 2pz1 in its excited state. So we require only 2 bonds about the carbon atom, that gives a sigma bond. See, this carbon with another carbon and this carbon with another hydrogen. So how many bond it requires to form? Only 2. So it requires the mixing up of only 2 atomic orbital. So one of the s orbital and one of the p orbital. The p orbital is especially 2pz orbital. Why do we consider 2pz orbital? Because the shape of the 2pz orbital is represented along the axis of the plane. That's why this 2pz orbital with 2s orbital of carbon that overlaps, that means that mixes up to give the sp hybrid orbital of carbon. This is the reason we are taking 2s orbital that mix with 2pz orbital, so it forms a sp hybrid orbital of 2. Both of them contains 1 electron each. And it has 2 more electrons in its 2px and 2py orbitals. Let us find the sp hybrid orbital. The carbon, it has 1 sp orbital in which one of the electron and the other sp orbital, it has one of the electron. This electron, the other sp orbital electron that overlaps with 1s1 orbital of hydrogen. Similarly, the second carbon has 1 electron in its sp orbital that overlaps with 1s1 orbital of hydrogen. So that makes s orbital with the sp orbital that overlapping is head on, that's why it gives rise to sigma bond, and carbon-carbon both they will share their one of the electron in its between them. So that makes carbon-carbon sigma bond. So to the plane, it makes the linear shape and it gets the bond angle among them is found to be 180 degree. So to which how the two pi orbitals are produced. Let us take carbon-carbon single bond. Both carbon atom, they have one electron in its 2px orbital and 2py orbital. This carbon also has 2px1, 2py1. See, the mixing of atomic orbitals has to overlap along, that is the side wave overlapping or the parallel overlapping. In such cases, only the 2px orbital can overlap with the 2px orbital of second carbon. Similarly, the 2py orbital of first carbon that has to overlap with the 2py orbital of second carbon. And during the side wave overlapping of 2px orbital and 2py orbital, one half of that 2py orbital that lies below and above the plane of the paper. But the side wave overlapping of 2px orbital that is lying in the plane of paper. So as a result, we can write the carbon-carbon, one of the bond that makes sigma, the other pi bond that lies in the plane of paper and the other pi bond that makes the part of above and below the plane of paper. So as to the presence of the two pi bonds between the carbon atom, that makes acetylenes are more reactive, and the structure that makes cylindrically symmetrical about the plane. So it approaches the linear shape. So when you draw a internuclear axis along this, it makes a cylindrically symmetrical shape. So this is what the structure of alkynes. The next one, preparation of alkynes. Alkynes that can be prepared from calcium carbide. This one, for industrial purposes, we can prepare or manufacture a large amount of acetylene. And from vicinal dihalide, geminal dihalide and the potassium salt of maleic acid. So let us take first of all calcium carbide. Calcium carbide is CaC2 that can be obtained from limestone. Limestone formula CaCO3. This is calcium carbonate. When it is strongly heated, it gives rise to calcium oxide and carbon dioxide. This is limestone. This is lime. When it is further heated with carbon, it gives rise to CaC2 and carbon monoxide. This CaC2 is called calcium carbide. So we can balance the reaction. Oxygen, here we have 2 carbon and 1 more carbon. So let us take 3 carbon in this reactant. And the next one, when this calcium carbide is hydrolyzed by water, H2O, this gives calcium hydroxide and acetylene, C2H2, or it is ethane. So this is industrial preparation. Industrial method, we can able to prepare the alkyne in large quantity. Then the next method from vicinal dihalide. Vicinal dihalide, the halogen in their adjacent position of carbon. So vicinal dihalide, we can have CH3, CHBr, CH2Br. So this is 1,2 dibromopropane. It has to undergo elimination. Elimination should take place between the adjacent carbon atom. So let us have first of all alcoholic potassium hydroxide that makes one of the HBr can be removed from the adjacent carbon atom. So the bond that can be moved into towards the carbon-carbon. So let us write, their formula will be CH3, C double bond, Br, CH2. And further it is treated with sodamide, NH2. This is called sodamide. So from this, one more HBr can be removed from the adjacent carbon atom. This is that HBr. So the double bond is now converted into triple bond. So we are getting CH3, C triple bond CH. This is propyne. So in vicinal dihalide, we have to make use of alcoholic potassium hydroxide for the elimination of hydrogen halide. So it involves hydrohalogen, that hydrogen and halide being eliminated. So we can say it undergoes dehydrohalogenation process. Similarly, we can prepare alkyne from geminal dihalide. What are called geminal dihalide? See, in vicinal dihalide, we have kept the halogen between the carbon atom of adjacent one. But in geminal dihalide, both the halogen to the same carbon atom. So the next method of preparation, we can take it from geminal dihalide. So geminal dihalide also undergoes dehydrohalogenation process. So let us take the compound CH3, CHBr and Br. This is 1,1-dibromoethane. This is first carbon, this is second carbon. Both the halogen at the same carbon. So it is called 1,1-dibromoethane. This is undergoing elimination reaction with the alcoholic potassium hydroxide. So that beta carbon, it has 3 hydrogen atoms. So one of the hydrogen that can combine with this halogen, successively the other hydrogen can combine with the next halide. So we can proceed. This is with the 2 steps. The first step, one hydrogen, one halogen removed. So I am getting a single bond into double bond with the CHBr. And in the another step, I am taking once again the alcoholic potassium hydroxide. In this case, this hydrogen and the halogen will be removed. So the double bond is into triple bond now. So we are getting CH triple bond CH. So every time when we remove the 2 groups from the adjacent carbon atom, that makes the single bond into their multiple bond. So this is what the preparation of alkyne from geminal dihalide. So the next method of preparation from potassium salt of maleic acid. Maleic acid is an unsaturated acid, CHCOOH double bond CHCOOH. When the hydrogen of carboxylic acid is replaced by K+ ion, we are getting potassium maleate. When it undergoes electrolysis, it gets splitted up into maleate ion and potassium ion. So at anode, the maleate gets liberated. So we can have CHCOO minus, CHCOO minus. It gets into the 2 negative, that is the electron, along with the 2 molecules of carbon dioxide, that is 2CO2 plus. We have both carbon dioxide group removed from adjacent carbon. So the double bond is into now triple bond. So we are getting ethine. So ethine that can be obtained from the industrial process from calcium carbide or from vicinal dihalide, geminal dihalide, as well as from potassium salt of maleic acid, or even we can take fumaric acid. Properties of alkynes. Let us see first of all physical properties. Just like alkanes and alkenes, here the first 3 members are existing in gaseous state and up to the next 8 members that are in liquid state, and the rest of all the alkanes will be in solid state. So just like alkanes and alkenes, alkynes can also be existing in all the 3 physical states, and they are generally colorless and odorless. But acetylene, it has some faint smell of garlic. Solubility, as it contains the triple bond in its structure, that makes the molecule weakly polar in nature. Due to its the weak polarity, that can able to soluble in water to some extent, that is sparingly soluble, or we can say slightly soluble in water. But they are readily soluble in organic solvents like alcohol, ether, etc. and their melting point, boiling point as well as the density, it goes increases with the increase in molar mass of the same homologous series. Let us find the next one, chemical properties. The chemical property, it discuss about the acidic nature of alkyne. What do you mean by acidic nature? A compound that can be characterized by its acidic property upon the tendency of losing the proton. So, we have the compound CH4, CH2 double bond CH2 and CH triple bond CH. So, CH4, it has sp3 hybridization, alkene sp2 hybridization and alkyne sp hybridization. So, when it moves from sp3 to sp, that is alkane to alkyne, the percentage of S character increases. So, the increase of S character, that increases the electronegativity of the carbon atom. So, electronegativity also increases due to increase in S character of the respective series. And hence, the hydrogen atom attached with the triply bonded system can easily be removed as proton compared to alkene and alkane. So, this makes alkynes are acidic. When they are acidic, the hydrogen should be bonded with sp hybridized carbon. For example, we can have CH triple bond CH, it is ethine. This is more acidic because the two hydrogen atoms, both of them are bonded with sp hybrid orbital of carbon. So, you can take the strong electropositive metals like sodium, which displaces the hydrogen from ethine, and we will get CHCNA. This is called sodium acetylide. This is sodium acetylide, or we can say sodium ethinide. And still it has one more hydrogen atom with its sp carbon. So, further it reacts with another sodium metal. The next hydrogen is being removed as hydrogen. Here also we can make the one hydrogen atom is removed. So, I will get CNA plus triple bond CNA plus. Both carbon, they have a negative charge since the sodium metal is much more electropositive, that is those are metal compared to carbon. This one is said to be disodium ethinide or disodium acetylide. So, as the difference of S character in sp hybridized carbon, the hydrogen attached to it gets more acidic nature and can be removed as proton. Instead of sodium, suppose if I take propine CH3 C triple bond CH, in which that can be, the hydrogen can be removed by using sodamide also. So, Na plus NH2 minus, in which this amine that abstract the proton from propine. So, we are getting CH3 C triple bond C minus Na plus the NH2 with the hydrogen that makes NH3. So, here we get sodium propionate. See that here the carbon, it has only one acidic proton, but the other carbon is bonded with the sp3 hybrid orbital of alkyl. So, in this you can't able to remove any of the hydrogen as proton. So, acidic proton we can find it only between the carbon-carbon triple bond system. Not only sodium or sodamide, the salts like copper 1 chloride Cu2Cl2, and it is present in ammonium solution, ammonium hydroxide solution, or silver nitrate in ammonia. So, these mixtures could also replace the acidic proton from alkyne. See, I have taken propine. This propyne, when it is treated with ammoniacal silver nitrate solution, this is also called as Tollens reagent. Ammoniacal silver nitrate is known as Tollens reagent. So the propyne, it has only one acidic proton. So the hydrogen that could be replaced by the metal. So we will get CH3 C triple bond C minus Ag plus. This is called silver propynide. Or we can take but1-ine. This is but1-ine, in which the triply bonded carbon, it has one proton, that is the hydrogen, that could also be replaced by the copper metal when it is treated with the copper 1 chloride in ammonium hydroxide. So we will get CH3 CH2 C triple bond C minus Cu plus. This is copper butanide. So this is copper. It has 4 carbon atoms. So but suffix ine, and it has a negative charge. That's why it is ide. So the name is butanide. But in the last case of the one, we have but2-ine. But in this, both of the triply bonded system have an alkyl substituent. It has neither H plus ion. So this but2-ine doesn't undergo any reactions with the metal or its metallic salt. So we can write it has no reaction, as it doesn't have that acidic proton with triply bonded carbon. That's all the acidic nature of alkyne. Let us see addition reactions. Addition reaction usually follows through the formation of vinylic cation. This carbon-carbon triple bond, when it is undergoing addition reaction with a general compound of HZ, where H is the positively charged one and Z behaves as the nucleophile, so HZ. As the hydrogen is proton and the one of the pi bond that can attack the H ion, so it forms the vinylic cation. So this carbon, it attacks, so the other carbon, that electron density decreases, and hence it makes a positive charge. This is called vinylic cation. This vinylic cation followed by addition reaction with the nucleophile that makes the compound. So in which during the addition reaction, the first step of addition of some compound, the triple bond is reduced to double bond, and successively we can add one more molecule of HZ to get a double bond into a single bond. So let us do addition of hydrogen. So hydrogen, it will undergo in 2-step to form alkane. So let's have CH triple bond CH, ethine. It undergoes addition reaction with the hydrogen in presence of nickel or platinum or palladium. So the first molecule of hydrogen that shares between the 2 carbon atom, so CH group changes into CH2 and the triple bond is reduced to double bond. Further, it can add with one more molecule of hydrogen that could also share between the 2 carbon atom. So we will get CH3CH3. So an alkyne is converted into alkane. This is addition of hydrogen. So an unsaturated compound gets into saturated compound. The next reaction, let us see addition of halogen. So the halogen, let's take here bromine. So when ethine is treated with bromine in carbon tetrachloride solvent, it undergoes the first step of addition to form CHBr double bond CHBr. And further, it undergoes one more addition reaction with one more molecule of bromine. So we will get CHBr2 CHBr2. So here the first case, the bromine are added to 1 and 2 position. So the name of the compound is 1,2 dibromo. Double bond is there. So we are getting ethene. But in the last case, it becomes a saturated one and the 2 bromine atoms are bonded to the same carbon. So this is 1, this is 1. So it is 1, 1. Sorry, this is 1, this is 2. So 1, 1, 2, 2 tetrabromoethane because of saturation. So this becomes 1, 1, 2, 2 tetrabromoethane. So this is addition of halogen. The next one, addition of hydrogen halide. Whenever we do the addition of hydrogen halide or addition of water or addition of sulfuric acid, whenever we do the addition reaction with such compounds, we have to follow Markovnikov rule. So if we have a symmetric alkyne, say acetylene, it may undergo the addition reaction with hydrogen bromide. It gives rise to CH2 double bond CHBr. And further it undergoes the next addition step with the HBr, where double bond is reduced to CH3 CHBr2. So this is 1,1-dibromoethane. Such halides are said to be geminal dihalide because both the halogen atoms are attached to the same carbon atom. So this is an example of gem dihalide. And the name of the compound, to the same carbon bromine is present twice the time. So 1, 1 dibromoethane. So for symmetric alkyne, the addition of hydrogen halide that can undergo to either of the carbon as it is symmetric about both the carbon atom. If we have an unsymmetric alkyne, say propyne, CH3 C triple bond CH. When we take the unsymmetric alkyne, the addition of HBr should follow Markovnikov rule. So according to Markovnikov rule, the negative group should go to the carbon with more alkyl, that carbon having more alkyl substituent. So this Br minus that attacks here, and this hydrogen goes to CH carbon. So we will get CH3 CBr double bond CH2. Once again it undergoes the addition of HBr. Similarly, the negative group, that is Br minus, that attacks to the carbon with more alkyl, and the hydrogen goes to less alkyl or no alkyl. So we will get CH3 CBr Br and the double bond into single bond to CH3. So here the name of the compound, the second carbon has 2 bromine atoms. So we can write 2, 2 dibromo, 3 carbon in a chain. So we will get propane. And the first one, 1, 2, 3. The first carbon has double bond, second carbon has bromine. So the name is 2-bromo prop 1-ene. Addition of water. Hydration of alkynes always carried out in presence of mercury 2 sulfate, or it is called mercuric sulfate, in presence of concentrated sulfuric acid. This reagent can also be represented as mercuric ion in presence of acid. Always gives carbonyl compounds, aldehydes or ketones. But only the ethane able to form aldehyde, but all other alkynes can give ketones alone. And during the formation of the carbonyl compounds, the addition of water that makes an intermediate known as enol. From this enol only the corresponding carbonyl compounds will be formed by the proton transfer. Let us see addition of water to ethane, CH, triple bond CH plus H2O. This possible in presence of mercuric ion and in presence of acid. So the water we can write it as HOH. One is proton, the other one is hydroxyl ion. So one will be a positive, the other will be a negative. See, the alkyne is symmetric, so we can add the H and OH to either of the carbon. So I will get CH2 double bond CHOH. This is called enol. En plus all, en due to the presence of double bond, OL, that is containing OH group, and this enol, it undergoes the proton shift that can be moved towards CH2 group that makes CH3 double bond into single bond, but the carbon oxygen gets double bond due to the shift of proton. So we have C double bond OH. So this is ethanol or acetaldehyde. So this is symmetric alkyne. We didn't follow Markovnikov rule. Let us take addition of water to propane on unsymmetrical alkyne. Let us take water as HOH in presence of Hg2 plus in acid medium, that gives the enolic structure of COH double bond CH. This is because the OH is the negative group that will go to the carbon with more alkyl substituent, and the hydrogen goes to the CH carbon. So we are getting CH3 COH double bond CH2. This undergoes the rearrangement by transferring the proton from OH to CH2 group. So the product formed CH3 CO CH3. It is propanone or acetone. The common name of the compound is acetone. So during the shift of the proton from COH to CH2, the single bond into double bond that makes between carbon oxygen, and a double bond into single bond that makes between carbon carbon double bond. So this is what addition of water. The next topic is polymerization. Polymerization, in the previous class itself we have discussed about a single monomer, the end time of monomer that can be converted into polymer as it contains all the molecules into it. That means yes, low molar mass of compound into high molar mass of compound. This alkyne that can undergo two types of polymerization. One is linear polymerization, the other one is cyclic polymerization. The cyclic polymerization gives aromatic compound. We will see the next one. Ethane that can be polymerized under suitable conditions to polyethane. I have taken n times of ethane molecule and n times of ethane molecule. See, the triple bond of the system, the one of the pi bond that moves between the two molecules of adjacent alkyne, that makes a single bond. So successively this triple bond goes to the next molecule. So such a way it can go linearly and it forms polyethane. So where the triple bond of ethane system is into double bond due to the movement of one of the pi electron to the successive unit of monomer. This polyethane usually conducts electricity. Under suitable condition we can make this polyethane as a conductor. So this is used as electrode in batteries. Where why do we use polyethane as battery? Because we are using the electrode as a thin film only, where the metal electrodes are much costlier, but the ethane is cheaper as well as lighter. So this polyethane can be used as electrode in batteries. The next, let us see cyclic aromatization, cyclic polymerization. So in this, when vapors of ethane is passed to red hot iron tube, we will get benzene. When vapors of ethane passed through red hot iron tube at 873 Kelvin. Benzene is a 6-membered ring, so it needs 6 carbon atom. So we have taken 3 molecules of ethane. See, the pi bond that moves towards the adjacent carbon atom, so it makes CH double bond, CH single bond, CH double bond, CH single bond and double bond CH with single bond. So that results in the formation of benzene, or we can write it as C6H6 with alternate double bond. So 3 molecules of ethane that may polymerize as cyclic manner to give benzene. This is called cyclic polymerization. The last property of alkyne is ozonolysis. Ozonolysis is nothing but the addition of ozone to an alkene or alkyne system. So here we are taking alkyne. So in alkene, the double bond only we had where the O3 it goes to COC, that ozonide structure is formed. As it has double bond, we got only carbon-carbon as a separate group. But in the case of alkynes, it has a triply bond system. The two bonds which are making that ozonide structure and one more bond is still intact with the carbon atoms. So this is what now ozonide for alkyne system. And this ozonide upon treatment with the zinc in water, that undergoes the cleavage of the same thing. Here it undergoes cleavage here and here. So the electrons of both all the three cleavages that makes a double bond between the CO group and one more double bond between the CO group. The oxygen which is left over, that makes hydrogen peroxide compound with water, so minus H2O2, where the carbon-carbon linkage we need to have. So we are getting CHO, CHO. This compound is said to be glyoxal. And this is highly reactive. So even in presence of the hydrogen peroxide, a mild oxidizing agent, the hydrogen peroxide which formed during the course of reaction, that oxidizes the resulting carbonyl compound into carboxylic acid. During that, the breaking of carbon-carbon bond takes place. So this CHO into COOH and this CHO into COOH. So we will get 2 times of carboxylic acid. So let us take the another example for this reaction. Propine, CH3, C triple bond CH. With ozone, it forms the ozonide structure CH3 with CH of this one. So carbon-carbon bond we have to maintain. So this is when treated with zinc in water, minus H2O2, hydrogen peroxide is formed due to the cleavage of carbon-oxygen bond and oxygen-oxygen bond. So that makes, we have the compound of CH3CH, C double bond O, CH double bond O. So a diketone is formed. This one, upon oxidation by hydrogen peroxide, the bond it gets broken between carbon-carbon single bond. So we will get CH3COOH, CH3COOH, and this one as CH3COOH. So how we are getting the OH group? Simple, the H2O2 that can be written like OH. So CH3COOH, HCOOH. Similarly here also we have OH in hydrogen peroxide structure. So that makes HCOOH, HCOOH. Here this is same carbonyl groups are there, identical carbonyl there. That's why we got the 2 molecules of same carboxylic acid. But here we have the 2 different carbonyl. So upon that reaction with the hydrogen peroxide, it gives 2 different carboxylic acid. That's all the properties of alkyne. The last topic of alkyne is uses of alkynes. So already we prepared that the polyacetylene or polyethylene by the linear polymerization, where we said the thin film of polyacetylene that can be used as electrode in batteries because of its lighter and cheaper nature. Similarly, ethine that can even be used in welding torches, that is in the form of oxyacetylene. That is the combustion of ethine that can give a very high amount of energy. Also in the manufacture of some polymers like polyvinyl acetate, polyvinyl ether, Orlon and neoprene rubbers. Then let us find the comparative study of alkanes, alkenes and alkynes now. We have completed the 3 different homologous series of hydrocarbon, alkanes, alkenes and alkynes. So this is the summary about the 3 forms of hydrocarbon. So all the thing whatever we discussed based on their structure, hybridization, S character, everything, it is tabulated here. So general formula we know that, and their common names paraffin, olefin, acetylene, and the first members is given, and what kind of bonding nature they have, single bond, double bond and a triple bond, and whether they belong to saturated or unsaturated, and their hybridization along with their shape, and bond angle with their carbon hydrogen bond length and carbon carbon bond length with bond enthalpy, and their percentage of S character. So this is what the summary about alkanes, alkenes and alkynes, the three forms of hydrocarbon. Okay students, we have completed our today's session, and the next session we will start with aromatic hydrocarbon. Until then, bye bye.